I'm ready to start, and I have a pleasure to present the supervisor of my PhD, Hristo Djidjev, which works last 30 years in Los Alamos National Lab, and he will present a talk about quantum computing and quantum annealing. It means quantum computing plus optimization. Okay, now we can start presentation.
Quantum computing, quantum annealing. So I'll try to present first some background information on quantum computing and quantum annealing, and then we'll talk briefly about some research problems and about type of research that can be done on quantum annealing. So let's go to the next slide. The talk will be divided into three parts. First, I'll talk about backgrounds of quantum computing, quantum annealing. The second part is about solving problems. So I will show how can you solve a problem if one has access to a quantum annealer. And as an example, we'll look at the maximum click problem. And finally, the third part is more research oriented. So how to address challenges of quantum annealing and, for instance, solving larger problems and improving accuracy of solutions and so on. Okay, so let's move to the next slide. So first I'm going to talk about background of quantum computing. And one thing Steph didn't say about me is that I have background in physics, and the reason is that I don't have background in physics. So that's unfortunate because mostly quantum computing is dominated by physicists. So I'm not one of them. So probably that will be an advantage because you'll be able to hear from a computer scientist. So maybe that will make it a little bit easier to understand. And also that will give me an excuse. So if I'm not able to answer some hard question about the physics behind quantum computing, I'll have an excuse, but I'll try to do my best to answer. So let's go to the next slide. Okay, so let's start with quantum information. And let's look first at the classical analog, the bit. It's the smallest information in the classical computing. So it describes a state of either 0 or 1, only one of them. And if you have n bits, they can describe any number between 0 and 2 to the n-1, but they can describe a single number at a time. The quantum analog is a qubit. So it represents one unit of quantum information, and we can think of it as being a superposition of 0 and 1, or as people say, it represents both 0 and 1. Specifically, the state of one qubit can be represented as a linear combination of 0 and 1. This is the cat symbol that that's around the number 0 and 1. This is what physicists use to describe some states. Okay, and alpha, beta are arbitrary complex numbers that should satisfy the condition that their squares sum up to 1. And those represent probabilities. Specifically, alpha square is the probability when we measure this state to get 0, and beta square is the probability that the measurement will give 1, and it can give just one of those two measurements, although the internal state is both 0 and 1. Okay, so when we have n qubits, n entangled qubits, in the quantum case, this represents to the nth exponential number of complex numbers. So this is the amount of information which is contained in the n entangled qubits. So for example, if we have 2 qubits, their states is described in this formula alpha 00 00 plus alpha 01 01 and so on. So unfortunately, I cannot point to the slide, but this is the line that's next to the last. And those 0001, the numbers in the cat symbols, these are the possible measurements. So for instance, 01 means that when we measure, we get 0 for the first qubit and 1 for the second one. And the coefficients give the corresponding probabilities when they're squared. Okay, so we have 4 bits of information describing 2 qubits, and when we have 3 of them, then we have 8 coefficients and so on. So we can see that there is a lot of information contained in one quantum register. So let's go to the next slide. Okay, so we have exponential number of information represented by n entangled qubits. So that seems quite the potential, but it's not easy to use that information. It's not easy to get to that information. So although we have those 2 to the n complex numbers, we cannot directly look at them. So the only thing we can do a measurement, and when we measure, we just get one number, one sequence of 0 and 1, and it can be any of them. The probability is determined by those 2 to the n complex numbers, but we cannot observe those numbers. We can just experience them when we do measurement of the qubits. The other problems that makes it hard is so-called decoherence. It is the interaction of the quantum system with the outside environment introduces different type of noises, and it very easily may lose its quantumness and behave classically, and then all those advantages disappear. The third issue is that programming is hard in the quantum case. We can use no conditionals. We cannot copy information or store information. We cannot print in the middle of a computation and such things that make classical programming easy. So the current technology, you'll see the term noisy intermediate scale quantum, doesn't offer yet any quantum advantage because of the relatively small number of qubits and because of the error rates, which are too high. So there are 2 major types of quantum computers right now. One is so-called universal, and the other is the quantum annealing computer. So let's go to the next slide. Okay, so first we'll talk about the universal or so-called gate model quantum computer. So the program for this computer is represented as shown on the picture. So each line corresponds to 1 qubit. So here in this case, we have 5 qubits. And then we have a sequence of transformations on those qubits. And you see that each transformation usually takes either 1 or 2 qubits, rarely 3, and never more than 3 qubits. And those are like one after the other. So we can observe that programming is quite straightforward. So there is no branching there. You cannot copy information or you cannot clone information. Despite of this, this has been shown to be advantageous compared to classical computing. So for instance, famous algorithm is the polynomial time algorithm for integer factorization. And there are other examples of problems that are probably solvable better on quantum computers and specifically on this model compared to the classical one. So this holds long-term promise, but currently the largest computers have only for about 50 and all less than 100 qubits, a relatively small number of qubits, and those qubits are noisy. Next slide, please. Okay, so the other type of quantum computer is, and the one that this talk is focused on, is the so-called quantum annealing model. So it's based on the fact that if we have a quantum system, it will tend to get into a minimum energy state, or if it is in a minimum energy state. And we want to use this fact to do to solve optimization problems. So the fact that this type of quantum computing is based on a so-called adiabatic theorem, so that there is a theoretical basis for this type of computing, and it basically states that if we start with a quantum system that is already in a minimum energy state, and you can always design some simple system that the minimum energy state is easy to find, then we can transform the system to another system that's of interest, quantum system. And if this transition is done sufficiently slowly, then the final system will also be in a minimum energy state. And here's the catch is in this sufficiently slowly. So actually for the hardest problem, sufficiently slowly means exponential time. So just this theorem doesn't give guarantee that we'll be able to do better using this type of transition, but if we do it more carefully, we can get some advantage. Okay, so to find a solution of an optimization problem based on this theorem, we can have the following steps. So first, we start with some mathematical problem, optimization problem, and we prepare some suitable physical quantum system that corresponds to our problem of interest. Then we make the quantum system transition to a minimum energy state, and then we go backwards, go from the quantum system to a mathematical one, and try to transform the parameters of the quantum system into values of the variables. Okay, so this is called quantum annealing, where the annealing term comes from. So let's go to the next slide. Okay, so annealing, this term is used in material science, and it means that if we have some material, we can improve the structure of this material. For instance, some glasses, some metals, we can get to their to their crystal structure by heating them and then letting them slowly cool down, and often we get to the desired effect. So in optimization, there is a famous method called simulated annealing. So probably most of you are familiar with it. So the way it works is the following. The simulated annealing works like this. So first, if we just do the easier so-called hill climbing, and let's assume this is a minimization problem. So the way we do it is we just move in the direction of improvement, here in the direction of getting lower values. And we'll end in a minimum, but unfortunately it can be a local minimum, and then we'll get stuck there. And for harder problems, there are exponential number of possible local minima. So simulated annealing is a way to avoid getting trapped in a local minimum by using the notion of temperature So if we at a certain point in our optimization and we have enough energy, we'll be able to jump from the current point to a point of a high energy. So in the top figure, this is illustrated as the point of low energy going to the high one. Okay, but if you don't have so much energy, then we remain in our local valley or our area. Okay, and in simulate annealing, we start with high energy, like we hit our our environment, so we're allowed to do bigger jumps. And as time goes on, then the energy and the temperature goes down, and we allowed to do smaller and smaller jumps until finally, basically, it boils down at the end at doing hill climbing. Okay, so the quantum analog of this is called quantum annealing, but it is done a little bit different. So at the top of the bottom picture, you have this flat area, and this is the initial state. So all those points, they correspond to the possible outcomes, so the possible values of the variables. And this means that all of those are equally likely to be picked. So any possible solution is equally likely to get at this point. And slowly, we modify this surface to get to the surface of our problem. And as we go by, if we do it adiabatically and slowly enough, as the shape of the curve changes, the probability of getting measurements with low energy increases. And when we get to the final state, which is at the bottom of the picture, so we have higher probability of getting a solution which is a minimum, global minimum, or close to the global minimum. So in quantum computing, you always have probabilities. So whenever you have a measurement, there is always a probability of not getting the solution that you want. But if probability of getting the right solution is large enough, then you can repeat the experiment and until you get the correct solution. And in optimization, you always can tell which solution is better than the other just by comparing the values. Okay, so this is basically the theory behind quantum annealing. So let's go to the next slide and see how I can solve some specific problems. Let's see about how we can get from the previous slide, how we can get the transition from this, from the top flat surface to the one that represents our problem, and how we can do it gradually by increasing the time. Okay, so let's go to the next slide. Okay, so first we start with some mathematical problem, and the mathematical problem that we can solve using quantum annealing is such a quadratic type of optimization problem. And we'll see that this is actually general enough, okay? So we have such problem to solve, and we can design so-called Hamiltonian operator that has a similar form to a mathematical problem, but instead of the variables, we have those so-called poly-Z type of operators. But what it means that this type of operator describes a quantum system that kind of represents our mathematical problem. Okay, and if we can if we can prepare this quantum system, then we have the first part of our final Hamiltonian. This is H sub PR. And the other part, so this is the part that represents the wavy shape, and the one that represents the flat line is by this Hamiltonian X sub EQ, which is the sum of so-called Pauli X gates. Okay, and then we do a linear combination of those two Hamiltonians, HEQ and HPR, by using time-dependent coefficients, which have the property that at time 0, only the first coefficient, A, is non-zero, equal to 1, and at the end, only the other coefficient is 1, the other is 0. So by changing the time from 0 to 1, our system transitions from the one being a flat line to one that responds to our problem of interest. Okay, so let's go to the next slide. Yeah, so this is the background information. So next we'll talk about how we can solve such problems in practice. So fortunately, it's not just a theoretical model, but we have the machines computers that can do such type of optimization, so-called D-Wave computers, which are based on quantum annealing, and D-Wave is a company in Canada. So there's several generations already of D-Wave computers. The D-Wave 2000Q computer, it's available in Los Alamos, still available. It has 2000 qubits. And the newest model, it's only available at D-Wave headquarters, and it has 5,000 qubits. So those qubits are implemented as superconducting devices. This is a regular chip technology that's used in other computers, but the trick that makes them quantum is the very low temperature. So on the bottom we have the picture of a chip. So it's not much bigger than a thumbnail, but on the top is the entire computer, and most of this computer actually consists of cooling devices because it has to be cooled down to 100 degrees Celsius above absolute zero, and it has to do other measures to isolate it from the environment, and it can do annealing times from 1 to 2000 microseconds. Okay, so how do we solve problems on D-Wave? So let's go to the next slide. Okay, so again, we have to reformulate our problem with whichever optimization problem it is. We have to formulate it in this form as minimum of quadratic form. So it has linear terms and quadratic terms. Hi, Aj are the variables of the problem here, and Ai, Aij are the coefficients. So the variables are binary, either -1, 1. So this is the so-called Ising formulation, or alternatively, they can be either 0, 1. This is a so-called Kubo formulation. So this is actually equivalent. It's easy to transform from one to the other. The Kubo formulation is usually easier to formulate optimization problems, and Ising is the one that actually is native to D-Wave. So usually you formulate your problem as a QO, and then it's transformed to Ising and submitted to D-Wave. Okay, so if you look at this quadratic form, it seems very restrictive. So first you have D-Wave only solving optimization problems, then you have only one type of optimization problems. So it seems too narrow, but actually with this type of quadratic function, you can encode any NP problem. So it's actually quite powerful enough. Okay. Okay. So the first step is the reformulating as a quadratic form. The second step is to map that problem into D-Wave hardware. So first we have to embed the structure of the problem. So we have to decide which variable goes to each qubit, and then we have to transfer the coefficients AI and AIJ to the parameters, hardware parameters. That's to encode those coefficients into the hardware. And then we do annealing, reading the solutions, and usually we do this into loop. As I mentioned, quantum computing is always probabilistic, but we have to do many repeats to get large enough sample of solutions, and then we choose the best one, which is easy to choose because it's an optimization problem. So the one that gives the best value is the best. Okay, next one, please. So I'll give here an example, the maximum click problem. So what is a click is a graph which has edges between any pair of vertices. So it's a maximally connected graph. That's a click. And if we have a graph, the max click problem looks at a subgraph that has a click, that's a click and is of a maximum size. So what is the click in the graph? That's a maximum number of vertices. Okay, and here, like if the animation worked, then I would have been able to show you the click in this graph, which is click of size 5. That's the maximum click of this problem, but I cannot see that. But just to give a simple example, so a click of size 1, of size 1 will be a simple vertex. Click of size 2 will be any edge of the graph. And click of size 3 is any triangle in the graph, and so on. Okay, so it's an NP-hard problem. So actually one of the first NP-hard problems that have one of the original 21 CARPS NP-hard problems. And it has multiple applications. Okay, so we have to solve some maximum click problem. How do we do it on D-Wave? So the first step is to reformulate it as a QO problem, and we'll do this on the next slide. First, we define a binary variable for each vertex, and the meaning of this variable will be like if we get 1, this means that the vertex is in the click. If we get 0, it means that the vertex is not the click vertex. Okay, so we're looking for maximum click. So our objective is to maximize the size of this set. And the size of this set is just the sum of all the variables because of the way it's encoded. And then our objective can be to maximize this sum of xi. Okay, so what is the constraint? The constraint is this vertex set that we defined forms a click. Okay, so what does that mean? It means that if we have an edge ij, then it means that xi and xj should be both 1. And this is equivalent to the product of xi and xj being 1. So you have the condition is that if xi, xj, the product is 1, then we should have an edge in the graph. Okay, so ij should be an edge in the graph. And it's easier to use the contrapositive version of this statement, which is like if ij is not an edge, then xi, xj is not 1, and that means that actually xi, xj is 0. So if we combine the conditions for all the edges of the graph, we have the constraint, which is the sum of xi, xj over all non-edges of the graph, or like all edges in the complement of the graph, should be 0. Okay, so let's go to the next slide. Okay, so this is 1a. This is the constraint formulation of the problem. it's an integer problem to maximize the sum of xi, and subject to the condition that the sum of xi xj over all edges of the complement of the graph is 0. Okay, so this is a binary problem. So this corresponds to b in the QO. And also it's a quadratic function. So xi is linear, xi xj is quadratic. So where does the u comes from? For u is for unconstrained, and this is not unconstrained because we have a constraint. So this is not entirely a QO. To make it a QO, we have to do one trick, which is to put the constraint together with the objective. And we do this in the formula on the bottom. So first we multiply the sum of xi by -1 because we want to make it a minimization problem. And we multiply the constraint by some large constant, positive constant m. And the idea is, so this works like a penalty. So since we want to minimize it, if the constraint is not satisfied, then the penalty is too large, and such choice of variables will not give a minimum. So in this way, we enforce that the constraint is always satisfied. Okay, so this is the QO formulation for the maximum click problem. And one thing that's not clear, how large we should put m. So fortunately, m doesn't need to be very large. Value of m equal 2 is large enough to guarantee that the constraint will always be satisfied. Okay, so once you have the QO, then we have just to map it on the hardware. So this is what we do on the next slide. Here we give just a simple examples. Simple example of problem with 3 variables. So we have 3 quadratic terms, and for each quadratic term, so we have first 3 vertices to represent this QO as a graph. We have 3 vertices for the 3 variables, and each quadratic term defines an edge. So Q1, Q2 defines an edge between 1 and 2, Q1 and Q2, and so on. So we have a triangle corresponding to the quadratic portion of the QO, and we don't need here to represent the linear terms. Okay, so we want to map this into the D-Wave hardware, and example of D-Wave hardware is this the picture on the bottom left. So this is the connection structure. This is the version of 1000 qubits. And because the problem is so small, we don't need the entire structure. We just need one cell, which is given in a zoomed form to the right. Okay, so to do the mapping, we map qubit Q1 to the corresponding qubit, and Q2 we also map to 1 qubit. But unfortunately, this cell and actually the entire connection graph doesn't have a triangle. So actually, there is no such qubit Q3 that will be able to connect to Q1 and Q2. So what is used here, and this is very almost always is used, is we connect 2 or more qubits together to work as a single one logical qubits. Here we have Q3 and Q3 prime representing the variable Q3, and we connect them with a large negative weight to enforce that Q3 and Q3 prime will take hopefully the same value at the end of the annealing. Okay, so such connected qubits that work as a single variable, as a single qubit, are called chains, and we'll be talking about chains later. Okay, so this is how the second step is performed. So let's go to the next slide. To run this on D-Wave is actually quite easy. To go back to our formulation of the maximum click problem, we have the QO given by the formula. So we have several parameters. So parameter H gives the linear coefficients. Here in this example, this will be all -1, the linear terms. The parameter J gives the quadratic coefficients. Here they'll be all +2, but only for pairs of qubits that are not in the edge set of the graph. The others are 0. Then we set annealing time parameter, which is anything between 1 and 2000, and number of reads parameter. As I said, we repeat the nulls many times, so usually it's between 500 and 10,000. And there are some embedding parameters that are related to how the QO is embedded in the hardware, but fortunately D-Wave provides software that can compute our embedding for us, so that's not an issue. Okay, next slide, please. Okay, so how well does it work? Does it solve all optimization problems to optimality? Well, unfortunately not. It depends on many things. So for larger sizes, it's less accurate than smaller sizes. For denser graph, it's less accurate than to sparser graphs. And also it depends just on the current state of the D-Wave. So sometimes the hardware works better and produces better solutions. Sometimes it produces worse one, and it's not clear how and why it happens. But it's interesting issue to study how the state of the computer itself changes in time, and actually it's one research problem that we are currently looking in. Okay, but in order to get better solutions, we can use some more advanced features of D-Wave and try to combine quantum and classical computing, which is actually the topic of the third part of the talk. So let's go to the next slide. How we can do better than just using the standards easy features of D-Wave in order to get better quality solutions. So we'll look at several examples. So next slide, please. Okay, so one issue we want to handle is the size of the problem. So on D-Wave 2000Q with 2000 qubits, unfortunately, the largest problem we can solve is the largest size of complete graph we can embed, which is about 65. So we can usually solve problems no larger than 65. And that's not a small graph, but what if we have graphs of sizes hundreds of thousands? So what can we do? Can we still hope to use D-Wave or another quantum annealer? So actually we could do in many cases, and this is using so-called subgraph partitioning problems approach, which is dividing the graph into smaller subgraphs and continuing recursively until we get graphs small enough to send to the annealer and then get the results back. And then from those subproblems, try to get the solution to the original one. Okay, next slide, please. Okay, so this is how it works for the maximum click problem. So this is the method of using single vertex partitioning. So we pick a vertex V, and there are two possibilities. So either this vertex can belong to a maximum click, or it may not belong to a maximum click. And for each of these two possible cases, we can simplify the problem. So if we know that V belongs to maximum click, then we just need to look at this maximum click, which will be formed by all, will be contained in a graph formed by V and all its neighbors. Okay, so we can remove V itself because we know it's already in that click, and just look for maximum click in the remainder of the graph. So this is graph G1 on the diagram. Okay, and the other case, possible case, is that V doesn't belong to any maximum click, and then we can just remove V because we know it's not in a solution, and remove all edges, and then we get the graph G2. So we know that the maximum click is in either one of those two graphs. So we can work on those small problems, and if they're small enough, then we just send them to the quantum annealer. If they're still too large, then we apply the same method recursively. Okay, next slide, please. Okay, so unfortunately, this can produce a large number of graphs. So in the worst case, it can produce exponential number of subgraphs. And we have to look at ways to limit the possible number of subproblems we can generate. So one way is to use so-called K-core of the graph. So if we know that our click has size K1, K plus 1, then we know that any vertex that has degree K or less cannot be in a maximum click. So it has too few neighbors, so we can remove that vertex. And when you remove the vertex, you also remove all edges to it, because you cannot edge without having both endpoints. And by doing this, we possibly reduce the degrees or the number of neighbors of the other vertices, and then you look for another vertex that has degree which is too small, and we remove it. And we iterate until all vertices of the graph has a degree at least K, and this is the K-core. So sometimes K-core can get rid of a large proportion of the vertices. So this is one technique you use. Another is so-called branch and bound technique, which uses lower and upper bounds to cut irrelevant branches, and irrelevant branches of the decomposition trees are the ones that we can figure out even without going through the branch, that it doesn't contain optimal solution, so we don't need to look into that branch, and I can also significantly reduce the search space. And the third method is so-called persistency analysis. This is another classical method that can figure out values of subset of variables. So we cannot solve the entire problem, but we can figure out that some variables, say x3, will be 1 in an optimal solution, or it will be 0 in an optimal solution, and then we can just ignore it. And the next few slides are about this actually persistency analysis, but because we are short the time, I suggest we skip them. So let's skip the next few slides, please. Okay, go next, go next, go next. Okay, so just to show here that we can combine several of those tricks. For instance, we can combine this decomposition method with this persistency method. And here in our experiments, we see that just using the persistency method can improve the performance by getting rid as few as 0%. So in one case, we cannot get rid of any additional variable, but in some cases we get rid of more than half of, sorry, not variables, but subproblems. In one case, we got almost 60% of the subproblems removed. Okay, next slide, please. Another technique is so-called spin reversal. So it's based on the fact that we can change the sign of a variable without changing basically the problem, having absolutely equivalent problems. So if you pick some variable xk we can replace xk by its reverse, minus xk. And here, in this case, actually, I have to point out that this is about the Ising portion of the problem where the variables can be -1 and 1. Okay, so if we flip the sign of xk, then in order to get the equivalent problem, we have also to flip the sign of ak and all akj quadratic coefficients, and you'll get absolutely the same problem, just in any solution, xk will have the opposite sign. So we're getting an equivalent problem. So what's the point of doing this? So the point is that there are some hardware biases in the hardware, and by changing the problem into equivalent ones, they're equivalent in mathematical sense, but in hardware sense that they're not equivalent, and some of them might perform better than the other one. So if we repeat this for several variables, then potentially we might get better solution. Okay, so the question is, however, how to choose which variables to flip. So there is exponential number of equivalent problems to the original one, and which one to choose of those exponential numbers. So let's go to the next slide. The way D-Wave does it, so it has a standard function, it just chooses a random set of bits to flip. And actually, even this simple version works in many cases, but our question is, can we gain anything if we try to optimize which bits to flip? And we researched this problem by using a genetic algorithm. So we tried to optimize the spin reversal transform. And it's a standard genetic algorithm. So we start with a random set of 0-1 bit strings. So 0 corresponds to the corresponding bit not being flipped, and 1 meaning that it's flipped. Okay, and we have a first generation of S of such bit strings. And then we do annealing with each of them, and then look at the solutions, and the one that have good performance we choose for the next generation. And we have so-called mutations where we randomly flip a small number of bits, and it is just a standard genetic algorithm. So we repeat until some faulting condition is met. And let's see on the next slide what results we get. Next slide, please. Yeah, okay, so here are some experiments that we did on 2 optimization problems, maximum click and minimum vertex cover. The first is in red and second is blue. And we see that the algorithm gets a big improvement after as few as 10 and up to 20 iterations. And after that, there is still improvement, but not so pronounced. So we can do significantly better than D-Wave's version, and much better than the version that doesn't do any spin reversals. Okay, next slide, please. Okay, another problem is so-called unembedding. So several slides before, we discussed how we can map a cubo onto the hardware. But after doing the annealing and getting the results, we have to map to the reverse mapping, to map from the hardware back to the original problem, from the qubits back to the variables. And when we have 1 qubit per 1 variable, it's easy. So whatever the value of the qubit is, that's the value of the variable. Like Q1 and Q2 in our case, we just copy the value. But Q3, so we have 2 qubits that represent Q3. And what if they get different values? So which of those 2 values should we choose as a value for the variable? And when we have a case like this, it's called a broken chain. And fortunately, it's not just having just 2 qubits in a chain. It's not typical. So usually have 10, 15, qubits in a chain. And it also happens that many of the chains are broken. So there are different ways to handle this. One is so-called majority vote. So we just look whether the zeros or ones are more, and if zeros are more, we choose 0. If ones are more, we choose 1. Another method is probabilistic methods. So we choose 0 with probability proportional to the number of zeros, and 1 with probability proportional to the number of ones. So it's kind of probabilistic version of the majority vote. And we have a version which is minimizing energy, which is like we decide for each qubit based on like greedy optimization. We choose the value that best improves the value of the objective function without that qubit. Okay, next slide. Okay, so what we did is by trying to design an algorithm that uses our knowledge that we know exactly what problem we're solving. So previous methods, they didn't know whether you're solving maximum click problem, minimum vertex cover problem, graph coloring, whatever problem we're solving, they don't know. So we showed in this research that by knowing our original optimization problem, we can design an embedding algorithm which is more accurate than the ones proposed by Djidjev. Okay, next slide, please. Okay, so we have here some comparison. So the bottom line is our algorithm, and it's compared to the D-Wave algorithms for different problems. So for the top left, maximum click problem, so this is the case where our algorithm, the performance is closest to the D-Wave algorithm. So we have only up to 5-6% improvement, which is not much. And here, the best performing minimized energy algorithm is actually almost as good as ours. But in other 3 cases, that same algorithm actually minimized energy works worse. That's the algorithm with the red line, I think. And the largest difference actually is in the bottom right corner, the graph partitioning, where actually our algorithm improved on the performance of all 3 D-Wave algorithms, almost 3 times improvement in the value of the objective function. Okay, next slide, please. And the last technique I'm going to talk about is using advanced annealing schedules. So the annealing schedules is how to mix the 2 Hamiltonians, the flat one represented by the straight line, and the wavy one that represents our objective function. How to mix them, and we did this by multiplying them by time-dependent function A and B. And actually on the top right figure, we can see the function A and B as used by D-Wave. And so the essential thing is that B is 0 in the beginning, and at the end, A becomes 0. Okay, and those are given by some, those are given in the interval 0, 1. We have variable S 0, 1, but the annealing time can be anything from 1 to 2000. So the way it works is we map our time interval into the interval 0, 1, and then use the corresponding value of S to see what are the values of function A and B. So this is the standard linear mapping from the time to those of function A and B, and in getting the Hamiltonian. But actually, D-Wave gives a possibility of using quite different and very interesting schedules. So actually, the function that maps the time to the interval 0, 1. Doesn't need to be monotonic, doesn't need to be linear. Actually, it can be very almost any function. So there are few restrictions, but there can be a very strange function given by some point. So you can discretize it and give a large variety of function. Most of them are probably not useful for anything, but some are. And one is represents the so-called quenching schedule, which is on the bottom left. So this schedule, like we follow the curves to some point, capital T, and then suddenly we end the annealing, like going all the way in just a single microsecond. We end the annealing, and that is the quenching schedule. So this schedule can be useful to see what possible happens at this time t. And we use it to try to understand how D-wave works, what happens during annealing. So as I mentioned, we cannot print from the anneal. Let's see what happens at time 1, time 2, and so on. So the only thing we can observe is what results we get at the end of the annealing. But using the quenching, actually, we can kind of stop the annealing at some point, print the result, and then produce slices of the anneal process at each time of interest, and then put those slides together and getting a picture like the one on the bottom right that shows how the energy changes during the anneal. So unfortunately, it's not so easy, because even this sharp end of the annealing shown on the bottom left picture is not steep enough, and actually a lot can happen during this short period to change the state at that point. But you use some trick to get over it and actually observe interesting things. For instance, here we can see that we have 3 phases of the anneal. The first one where it's mostly flat, then a short phase of here only like 20-30 microseconds out of 1000, where most of the action happens, and then again we have a flat phase, and actually this is quite typical. So we always have those 3 phases, but they vary. So like the angle might change of this vertical phase. We might have more variation in the flat phases, but more or less we have those 3 phases that we didn't know about before. Okay, next slide. Other approaches that I don't have time to discuss. So for instance, we can insert a pulse. We can do reverse annealing, so like starting from some known solution, and as a result, we can kind of limit the search for solution and in the area of some good solution that we are aware of. We have done some annealing parameter optimization. We have tried to mitigate some persistent hardware biases by modifying the coefficients. So in order to get rid of some bias, we can slightly change the original coefficients of the Cubo version in order to neutralize, to mitigate the effect of those biases. And finally, recently used machine learning to predict the hardness of a problem, and based on that to allocate more resources, which might be like longer annealing times. It can be a larger number of anneals, so that we can get better results for harder problems. Okay, next one. Okay, so to conclude, quantum computing is definitely some very exciting and promising long-term area for computing. but unfortunately, the current quantum devices are too noisy, too small. So we cannot see any advantage currently for solving problems of practical interest. And this is both for all models of quantum computing, for all available quantum devices. Regarding the quantum annealers, so the good thing is that we can actually program those computers. D-Wave commercially sells them for people that have money to buy them. They're quite large in number of qubits, almost 100 times larger than corresponding universal quantum computers. But still, they have limitation that they work only for optimization and sampling problems. So this is what makes those makes it possible to have computers with larger number of qubits. And also, they're still susceptible to noise, and although large, their number of qubits is still limited. So one can handle those limitations by designing hybrid classical quantum algorithms. And we show here how we can do decomposition algorithms for solving larger problems. You can use spin reversal, transform, or use some advanced schedules. Okay, next slide, please. Okay, so some of those works that were done with my collaborators, Elijah Prilovsky from Los Alamos, George Hahn from Harvard University, Aaron Barbosa from University of Texas, and Guillaume Risque and Guillaume Chapuis from University of Rennes. And on the next slide, you can see a list of some recent publications. Thank you for your attention, and I'll be happy to answer any questions.
Thank you for your very interesting presentation. Are there any questions?
Okay, so in one of the last slides, you said that they are easy to program, but at the beginning, you showed something like that looked like a something for a musical score as a way of programming. So
Right.
I am absolutely have no knowledge of quantum computing, but how do you program a quantum computer with 5,000 qubits? Do you have 5,000 lines and you are drawing little like perpendicular lines to describe the programs, or are there already advanced tools that you express things in a more understandable and usual way?
Okay, so let me draw a distinction. So the slide with that musical score, this is for the quantum universal quantum computing or the gate model computing. So this one are harder to program. This is universal, meaning universal here means that anything that you can do on classical computer, you can program and do on those computers, at least theoretically. It's not so easy, but you can do it. That has been proven. So they're at least equivalent to a Turing machine, but it also has been shown that you can do actually things that you cannot do as efficiently on a Turing machine. But this is the gate model or universal model quantum computers. And when I said these are easy to program, I'm talking about the quantum annealers. So to program a quantum annealer, if you just want to solve any problem on quantum annealer, you just need to design your qubit. So you have a combinatorial problem, you have to reformat it as a qubit, which is a quadratic version. And it's so for the most interesting problems, this already has been done. One knows how to program like maximum click, minimum vertex cover, graph partitioning. So all those basic problems, it's known how to program as a qubit. So this is the only thing that you need to figure out, and then you get this this matrix of coefficients, and all you have to do is send this matrix of coefficients to D-Wave, and D-Wave will do everything else for you. So it will scale down the coefficients, it will map it to the hardware, it will do a number of anneals depending on what you want it. Like you want it to do 5,000 anneals, so it will do 5,000 anneals. You said, I want to have each anneal last hundreds microseconds. It will do that for you. It will read back the results. It will do an embedding, and it will give you 500 samples, 500 possible solutions for your problem. And you can pick any of those 500 solutions, which probably you don't want to do, but the better thing to do is you look for each solution, what value it gives to your optimization problem, which is classical thing to do. You can do it using Python or whatever you like to program with. And you say, okay, I solve a problem on a quantum computer. So there are two things that you need. First, to program to represent your program as a matrix of cubic coefficients. And second, you need an access to D-Wave. And D-Wave gives limited access to most people. Limited means that you have like that many times you can use it in a month, but anybody can do it. The gate model it's quite different, and it's quite more difficult. And those have
thank you
about 550 or less qubits.
Any other question? I see that there are enough participants which can ask something. If no more questions, thanks again to Professor Djidjev for his very nice and interesting presentation, and hope that you will participate again in the next issue of this conference.
Thanks everybody for attending my talk.
Thank you very much.
Thank you to all participants to participate here.